There are three principal ways of transmitting tractor engine power into useful work. Of all those three, first one is power takeoff. The second was being hydraulic. The third one being drawbar. So these three are the principal ways. Principal ways. And on which the least efficient and the most used method is the drawbar. So drawbar is the least efficient and still the most used method. So of all the three, drawbar is the least efficient and the most used method. The basic configuration of wheels and tracks are modified to meet the special operating conditions in various parts of the world. The predominant so the predominant the predominant traction device is the pneumatic tire. The P is silent in this one. Pneumatic tire. The majority of terminologies which we are going to use in this one will be taken from the ASAE. What is ASAE? ASAE. Actually, they are the pioneer when it comes to the different type of uh, innovations and discoveries in the farm sector. So ASAE is nothing but American Society of Agricultural Engineers. So this is a full form of ASAE. Traction is developed. So few things are, let me just write which is beneficial. Few points. Traction is developed by Traction is developed by the interaction of mechanical devices with soil. Okay, so what happened at the central to design of the traction system is the development of the performance equation. So in the year 1985, in the year 1985, one scientist, his name is Free, F-R-E-I-E, Freitag. What he did, he indicates that performance equation performance equations have developed by the use of theoretical analog and empirical approaches. So yeah, theoretical, oh shit, yeah, theoretical analog and empirical approaches, Freitag in the year of 1985. Owing to the complexity of the soil traction device interactions, the theory approach has not yielded readily usable solution for the designer. However, it does provide general performance response for a particular combination of soil vehicle parameters. So that was the issue. But later on, one scientist, his name was Mohr. Coming to the next page. So Mohr-Coulomb failure criteria has came up. Okay, let's give a headline. I think 2.4 would be good. Which color? Let's choose this color. Mohr So this criteria is generally used for, let me write in one sentence such that it is clear, but I will elaborate as well, to determine shear force corresponding to corresponding to various vertical loading. So actually this Mohr-Coulomb failure criteria, it is the application of, like the application of the Mohr-Coulomb criteria is to a soil plate lug situation, provides insight into the nature of the plate, that is the lug loading, and the soil shear behavior. So it would be better if I just draw a picture and try to Okay. Yeah, I think it's better to draw a picture. Not that good in the drawing, but let's see how. Yeah, if this is B and there is load W, okay, wait, let me make it more. So what happened that there is a this is called soil plate lug. Okay, this is called soil plate, also called the lug. Okay, so what happened that when we put the load W, the load W, after putting the load W on like the breadth of the soil lug is L, B, and the length is L. What happens when we perform when we put a force F, then we see that the lug is moving the distance of x. This x is nothing but the deformation. When we suppose that there's a lug like soil is between all these things, all these uh, yeah, soil is here, and weight is given, so soil will try to resist that it should not move. And we know that the Newton's law, uh, everybody wants everybody wants to continue the state of the motion. If it's a rest, it will try to continue in the rest, and if it's in motion, it will continue motion until unless some external force is applied. So when it is on the stationary position, these lugs, this is holding the soil. But when we apply force F, we see that after W is the weight which we are applying. After the force X, this is deforming X. So this is the finding of Morse, in which he told that the force F, which we right now written over here, F is the function of AC plus W tan phi. So let's just first of all write the terminologies. What does what means? So starting with the F, where F equal to failure shear force, or sometimes it is called soil thrust. It is the maximum value of shear force that causes failure of the soil. So that's why it's called the failure. After A, the next thing is A. A is nothing but the area of shear. And coming to the next is C. What is C? C is nothing but the cohesion strength of the soil. Kilopascal or megapascal. In any unit, it can be W, normal force. And the last one is the phi. Phi is nothing but the angle of internal friction. So what happens that Morse, what he did, he tried to change the dimension. Sometimes he will increase breadth and length, which will do what, it will increase the area. So the more the area, the more will the cohesion. Okay, because of which we can see F equal to AC plus tan phi. If A will increase, F will increase as well, because F is directly proportional to A over here. So area will increase, the cohesion will increase, the friction will increase, because of which the soil failure will be less. W, if W is more, then the lux will go more deeper inside the soil, such that the soil will have more strength, or more soil will grip the lux very nicely, such that it won't move nicely, it won't move very easily. So F will be equal to, so after doing a lot of experiment, he came to know that F is equal to AC plus W tan phi. So yeah, till now we have read about these two things. Let's read something more. So while doing this, what he did, as I already told, he tried to change a lot of things, and then he found out few things. So there's one graph which is very famous. He, like from the previous equation, F equal to AC plus W tan phi. So when he tried to make a graph, or he, what he did that he increases the W and check what is the value of F. So the graph, or the, here it is, so the graph something looks like this, something in this format. So this is the force axis, and this is the x-axis. X-axis, which is the deformation. This is the deformation here. This axis here, the deformation. So we make a graph putting F and X by changing the value of W. So if, what happens that if you put W1 force, if you use W1 force corresponding to that, if we apply F1 force, then we came to know that the X1 is the deformation. Once we increase the W2, W1 to W2, then the force will also increase, and in that condition X2 increase as well. W3, it will become X3, and this become X3, which means that we find that the soil having some cohesion, that force F doesn't approaches 0 as W approaches 0. If the maximum value are plotted for a soil that has both cohesion C and internal friction phi, the result will be similar to this. So after this graph, we did one more graph. This is the F versus X. So let's keep it here only. Okay, and then what we did, we make one more graph, and this time we plotted the graph between F and W. These two graphs are one of the most important graphs. So this axis is nothing but the maximum pull force. That is F. And this is nothing but the normal force W, which we are so, and this distance is nothing but AC. And when we try to find out the slope of this line, we found it to be 5. This one is F, F1 corresponding to that W1. This is F2 corresponding to that W2. This is F3 corresponding to that W3. So this is a figure from where we can understand what does the Mohr did. So what actually happened, that even if you try to bring W1 to 0, we will, what we find that the moment, see, if we bring W1 to 0, first of all W1 to this one, then there is a corresponding value something F0, then here W minus 1, so F minus 1. But as we reaches W to 0, there is a fixed value, there is a fixed value of F, which is never being like, which always used to come. So that F value is nothing but F0 is nothing but F0 is nothing but when we apply W0 force, and which is equal to AC. So this is nothing but the y-intercept. And after plotting this graph, we find out, like we all know how to find the, just bring it here, theta is nothing but this one, or if you want this one, this total, you can use this one also, this length, and then also you can find out the, this one will be F2 minus F1, this one will be W2 minus W1, and tan phi equal to nothing but F2 minus F1 upon W2 minus W1, theta equal to tan inverse F2 minus F1 upon W2 minus W1. So that is also we can do, or we can just extend this one. Similarly, it's not different. This one will become W2 minus W1, this one will become F2 minus F1, and this is theta. So this is how we can find out the theta value of the theta. And theta, after calculating, we came out to be, this is nothing but the angle of, here we have written, theta is angle of internal friction. So with this value, modes have defined this. And in other terms also, how we can represent the same thing is with the value of, sorry, stress and shear strength of the soil. So the formula, which was F equal to AC plus W tan phi, if we divide all the both side of the equation by A, F upon A equal to AC upon A plus W tan phi upon A, if we change, then F upon A is nothing but tau equal to A, it will be cancelled out, plus W upon A is nothing but the stress. Okay, so let me just put it down. This is This is what shear strength of soil. Okay, and this one is normal stress. Why normal stress? Because it the force which is being applied, this is the normal. Okay, normal to the surface, that's why it's called the normal. So here is strength of the soil and normal stress, or it can be called normal soil pressure. Normal soil pressure. And yeah, this equation it can be written as F equal to AC plus W tan phi